So we're going to take all of the information that we know. We're going to use our circle here, and we're going to split it up into different families. The first family we're going to look at is our axes family. And we'll start in degrees and say, I know that this angle here on the x-axis is 0 degrees. And I'm going to try and write my degrees always in the same place. So on this axis, does this make sense that this would be 90 degrees? On this axis, we'd get 180 degrees. This axis would go all the way to 270 degrees. And if we went all the way around, we'd also have 360 degrees. Now we're going to look at putting these same angles in radians. So on this axis, we'd have 0 radians or 2 pi radians, because 360 degrees is 2 pi. 180 degrees, that's pi radians. 90 degrees is half of pi, so pi over 2. And since 270 degrees is 390 degrees, 270 degrees is 3 pi over 2. This is the axes family, so these are the points on the unit circle where the unit circle and the axes intersect. And we are able to label those points because the radius of the unit circle is 1. So this point here, the x value would be 1, the y value would be 0. This point up here, the x value is 0, the y value would be 1. Here we would have negative 1 comma 0, and here we would have 0, negative 1. And now the mental math questions can start, because now you can do sine of pi without your calculator. How do we do that? Well, the coordinates, one of our big ideas, what all coordinates on the unit circle are cos theta comma sine theta. So if I want to find sine of pi, all I need to do is think of pi. This is my angle pi. Here's my coordinates. My coordinates at the angle pi are negative 1 comma 0. Sine of pi would be negative 1 or 0. Well, according to our big idea, your y coordinate is sine. So sine of pi, I'm looking at my y coordinate at pi, sine of pi will be 0. If you type that into your calculator, it'll tell you the same thing. If you type cos of pi into your calculator, you'll get negative 1. Sine of 90 degrees, 1. Cos of 90 degrees, 0. Cos of 270 degrees, 0. Sine of 3 pi over 2 radians, negative 1. And so we can figure out all of these values without our calculator just by looking at the coordinates. We can also figure out tan. And I'll write tan of 0. Well, tan is sine divided by cos. So if I take my y coordinate and divide it by my x coordinate, what's 0 divided by 1? 0. If I go over here and do tan of pi, what's 0 divided by negative 1? 0. If I go up here and do tan of pi over 2, or tan of 90 degrees, take my y coordinate divided by my x coordinate, 1 divided by 0. What's 1 divided by 0? It's an error. And so what we'll write on here is undefined. It's not possible. If you type it into your calculator, tan of 90 degrees, you'll get an error. If you type in, if you're in radians and you write tan of pi over 2, you'll get an error. And same thing down here, when I try to do tan of 3 pi over 2, it's also undefined. And so here's our first family, the easiest one. All of your axes. Coordinates were easy to label. Tan is just sine over cos. You can look at your coordinates to figure out tan. All of these values are right there. And so now we can do sine, cos, and tan of all of those angles in radians or in degrees. Our second family is the pi over 4 family. And in the space, you have some space up here. What I'd like you to write down is special triangle for pi over 4 or 45 degrees. Because we need to figure out sine, cos, and tan for 45 degrees without our calculator. So how do we do that? Well, if we're trying to figure out sine, cos, and tan, we're going to need a right-angled triangle. And if I draw a right-angled triangle and I make one of the angles 45 degrees, what's the other angle? 45 degrees, because it has to add up to 180. So what kind of triangle is this? Besides being a right-angled triangle, it's an isosceles triangle. And what do you know about isosceles triangles? Not only are the two angles the same, but the two sides are the same. I know that this side here is equal to this side here. And since the power of trigonometry is it doesn't matter how big or how small that triangle is, sine of 45 is always the same. Cos of 45, your calculator always gives you the same answer. So I can pick any number I want for the side. If I want my math to be easy, I might choose 1. But it will work if you choose 5, if you choose 2,000, it'll work. So if I choose 1 for one side, since it's isosceles, the other side has to be 1 as well. And I can do a squared plus b squared equals c squared. What's my hypotenuse? Square root of 2. 1 squared plus 1 squared is 2. My hypotenuse will be the square root of 2. From this, what does this give me? I now know what sine of 45 is. Move this over. Well, sine is opposite over hypotenuse. The opposite side is 1. My hypotenuse, root 2. And when we write our values on our unit circle, we're going to rationalize. Remember, to rationalize the denominator, you could multiply the top and bottom by root 2, and this would give you square root of 2 over 2. But if you're asked what's sine of 45 degrees, you're allowed to write 1 over root 2 or root 2 over 2. Either are fine. What's cos of 45 degrees? It's also the same, 1 over root 2, which if you rationalize it, becomes root 2 over 2. And what's tan of 45? It's equal to 1 over 1, which is just 1. We did all of that without a calculator. Just drawing a special triangle, labeling our angles, picking an arbitrary length for the side. If you chose 2 and 2 and got square root of 8, if you reduced that to lowest terms, you would also get root 2 over 2. So now what we're going to do is we're going to go back to color coding, starting with degrees. This is your 45-degree family. What that means is your reference angle for each of those angles is 45 degrees. So if my reference angle is 45 degrees, it's pretty obvious that this one in quadrant 1 will be 45 degrees. If my reference angle is 45 degrees, can you see that this is 135 degrees? And now I give you a 5-second head start to do the last two before I write them down. If you want to just write them on scrap paper, if you think you're going to get it wrong, you can do that. But if you just want to do mental math and have it in your head. Did you get 225 degrees and 315 degrees? Now we go to our radians. It's the pi over 4 family. So in quadrant 1, we'll have pi over 4. In quadrant 2, if the reference angle is pi over 4, how would you figure out what this angle is? Well, if it was degrees, you did 180 minus 45. So in radians, you're going to have to do pi minus pi over 4. And how do I subtract fractions? I need a common denominator. Pi is 4 pi over 4. Subtract your pi over 4. We're going to get 3 pi over 4. Again, I'll give you a 10-second head start to do the other angles. How did you do? Did you get 5 pi over 4 and 7 pi over 4? Label your coordinates on the unit circle where these angles intersect the unit circle. The coordinates of our first one are root 2 over 2 and root 2 over 2. Why? Because your x-coordinate is cos of 45 degrees, and your y-coordinate is sine of 45 degrees. And from our special triangle, we know that cos of 45 degrees is root 2 over 2, and sine of 45 degrees is root 2 over 2. So those become our coordinates there. In quadrant 2, it's the same triangle. It's the same reference angle. So sine and cos are going to be the same, but in quadrant 2, cos is negative, sine is positive. Makes sense because can you see that if I went to quadrant 2, my x-coordinate would be negative because I'm going left. My y-coordinate would be positive because I'm going up. So you can see why the cast rule works. Because if your x-coordinate's cos, it has to be negative in quadrant 2. In quadrant 3, can you see that both your x and y coordinates would be negative? But since it's the same triangle that's made back to your x-axis with the same reference angle, your sine and cos will both be root 2 over 2, but now they're both negative. And in quadrant 4, your x-coordinate would be positive because cos is positive. Your y-coordinate would be negative because sine is negative. And finally, when figuring out tan of pi over 4 or tan of 45 degrees is 1. You can see that from your triangle. You can also see it by taking sine divided by cos. If you take root 2 over 2 and divide it by root 2 over 2, you're going to get 1. Tan of 3 pi over 4 is going to be negative 1. It's going to be the same value because it's the same triangle. Cast rule says tan is negative in quadrant 2. If you did sine divided by cos, you'd have root 2 over 2 divided by negative root 2 over 2. You'd get negative 1 that way as well. Tan of 5 pi over 4. Well, tan is positive in quadrant 3. If you did sine over cos, you'd have negative root 2 over 2 divided by negative root 2 over 2. That would be 1 as well. And finally, tan of 7 pi over 4. Is equal to negative 1. So what's starting to happen, hopefully, is you're starting to see, oh, why the cast rule works can be described by the unit circle. the big idea that points on the unit circle are cos theta comma sine theta explains a lot of things with trigonometry when you go into angles past 90 degrees. Turn the page over. Again, in the space that you have in between pi over 3 and pi over 6, in this space right here, is our special triangle for pi over 3, pi over 6, or 60 degrees and 30 degrees. Because again, we need to be able to calculate this without our calculator. So I'm going to make a right angle triangle. I'm going to label this side as 60 degrees. And the reason it's the same triangle for pi over 3 and pi over 6, or the same triangle for 60 degrees and 30 degrees, because if this angle is 60 degrees, what's the other angle going to be? 30 degrees. This is a right angle triangle because we have 90 degrees. What's the name of this kind of triangle otherwise that has 3 different angles and 3 different sides? Do you remember the name? Probably not. Because of all the, special, when you think of special triangles, you think of isosceles. You think of equilateral. Those are special because all the sides are the same, 2 angles the same, 2 sides the same. We have a name for this triangle. It's called scalene. And the name itself is sort of like you're not special. You have all things different. It's like the not special triangle of the world. And that's why you forget the name of it. Because it's like everything's different. Why is this special? So this not special triangle is feeling very bad because right now, do I know anything about the sides? No. It's not special whatsoever. It's like, oh. So this triangle right now, it's pretty sad. And it goes walking around all sad. It's like, I'm not special. And it runs into another scalene triangle just like it. Are you special? No. Are you special? No. They're like, yeah, well, you want to hang out? Okay. So the 2 triangles get together, and so the other non-special triangle comes over here. It's exactly the same. It's got 30 degrees here and 60 degrees there, and they get together. But once they get together, what do they make? Together, we've got an equilateral triangle here. Those 2 triangles together make an equilateral triangle because all the angles are 60 degrees. All the sides would be the same. And so what we realize is if I make this side 2, then this side over here is 2. And since they're the same, can you see that this side has to be 1 and this side would have to be 1? And I can pick any arbitrary lengths, but because they're the same, this side is going to be half of that hypotenuse. If you did a squared plus b squared equals c squared, you could calculate the height here. 2 squared minus 1 is 3. This side will be the square root of 3. And now, we can now figure out sine, cos, and tan of 30 degrees. And we can also figure out sine, cos, and tan of 60 degrees. Well, how do we do sine? Well, it's opposite over hypotenuse. When we look at 30 degrees, the opposite side is 1. Hypotenuse is 2. So sine of 30 degrees is a half. What's cos of 30 degrees? Adjacent over hypotenuse. Square root of 3 over 2. And what's tan of 30 degrees? Opposite over adjacent, 1 over root 3. Again, When we write it on our unit circle, we're going to rationalize our denominator. So just a reminder of how to do that. Multiply top and bottom by root 3, and you'll get root 3 over 3. When doing questions, you have to be able to recognize that root 3 over 3 and 1 over root 3 are the same thing. Because sometimes you'll get 1 over root 3 in a question, sometimes you'll get root 3 over 3. Sine of 60, cos of 60, tan of 60, same thing. We can look at 60 opposite over hypotenuse. Cos of 60 adjacent over hypotenuse. Tan of 60 opposite over adjacent. And our special triangle let us figure out sine, cos, and tan of 30 and 60 degrees. Well, I guess one special triangle didn't help us, but it's only when those two got together and commiserated that we were able to figure this out. So if we go to our circle and start labeling things, starting with what we're comfortable with, degrees. Here's our 30-degree family. All the reference angles are 30 degrees. So the second angle, if this is 30 degrees, 180 minus 30 degrees, 150 degrees. Again, 5-second head starts on the last 2 degrees. How did you do? 210 degrees, 330 degrees. Again, your challenge is to mentally get it before I put it up there. Now in radians. This angle is pi over 6. In quadrant 2, if you did pi minus your reference angle and got your common denominator, you would get 5 pi over 6. 10-second head start on the radians. Seven pi over 6 and 11 pi over 6. Draw your points on the unit circle. Look at your special triangle. At 30 degrees, points on the unit circle are cos theta, comma sine theta. So cos of 30 degrees, root 3 over 2. Sine of 30 degrees, 1/2. Once you know quadrant 1, the same family is going to have all the same coordinates. What's going to change is whether they're positive or negative. Same thing with tan. From your special triangle, tan of pi over 6 is root 3 over 3. And that's going to stay the same except for positives and negatives. In all 4 quadrants. All right, we'll do some mental math. You might have to flip your page a little bit. What's tan of pi over 4? Evan, pick a volunteer. Tan of pi over 4. Sam, what's tan of pi over 4? Might have to flip your page back to the one before to look at your pi over 4 family. You can write this down after, so. Tan of pi over 4. Yes. Okay, Sam, pick someone for cos of 7 pi over 6. Lauren. Negative root 3 over 2, just your x coordinate right there. Perfect. Pick someone for cos of 270 degrees. Haley. Zero. Excellent. Haley, pick someone for sine of 330 degrees. Negative 1/2. And the last one, pick someone for cos of 5 pi over 6. Avery? Simon? Perfect. And now we're ready to finish up our last family, but we're seeing how powerful all of this is. We can quickly figure out values just by looking at coordinates on our unit circle. The last family is a 60-degree family. In degrees, it's 60 degrees. In radians, it's pi over 3. 25-second head start. All right. How did you do? Did you get 120 degrees, 240 degrees, and 300 degrees? And in radians, whoops, that's not green. 2 pi over 3, 4 pi over 3, 5 pi over 3. Labeling your coordinates. Quadrant 1. From your special triangle, cos of 60 degrees is 1/2. Sine of 60 degrees is root 3 over 2. Now our values are going to stay the same. All that's going to happen is what stays positive and what changes to negative. And finally, tan